Swayam Prabha. Digital India. Educated India.
I'd like to look at an interesting example with, we're going to come back to the market shed frame and look at some solutions in Consteel. So we had done the market shed frame and looked at how we could do first order solutions with amplification factors yesterday. And the base market shed frame file that's out there, so rather than building things from scratch again, most of this is what you've done already with the L frame if you were going to model the market shed frame. And so let me bring that up and let's talk about it. I'm going to turn these off. If I get my okay, so we've got that view of our frame here. So it looks a lot like the L frame that we did before, but this is a sway frame now. And so we've got the out of plane bracing similar to the L frame. They are top and bottom flanges on the roof girder. We've got simply supported boundary conditions in plane but resisting twist there at the base. And now in the market shed frame we have an HSS column here on this end that's supporting the so-called right end of the roof girder. Now remember when we did our model of the market shed frame yesterday, we had a pin. Now a few subtle there at the top and bottom. A few subtle things with that. The pin was basically at the location of the reference axis or centroidal axis of the roof girder in what we modeled in the analysis model I showed you yesterday, which is kind of a typical approximation that we often would use in engineering design. So if I kind of look at this one, let me go to that. I like that representation better. So here, kind of similar things. We've got the frame wizard model of the panel zone area there on the left. But what I've done here is in modeling the HSS column, I'm only modeling that column to the bottom of the roof girder. Okay? And in that column, let me turn off the portions menu there, and let me pull up okay, I got object property, that's good. So I'm going to select that HSS column so we can inspect the object properties there. So notice I have a release start endpoint. That's the start is at the bottom. That's continuous, but I've got supports there that are basically pin supports at the bottom. But at the top, I've now changed that from continuous to XX, YY, ZZ, W. That means I'm releasing all rotations continuity between the top of the HS section and the bottom of the roof girder. Now maybe that's overdoing it a little bit. Possibly the ZZ should be continuous, and then we say, oh yeah, we're going to model the connection to the bottom of the roof girder as a pin. How did I get that? If I look at the ... menu here, menu button, and click on that, I can see it shows me what that particular constraint is, or that particular modeling condition is. means, okay, so I'm continuous for the displacements x, y, z, but all the rotations and the warping continuity are released from whatever I'm connecting to at the end of that member. Okay? Now, how did I get that when I modeled the frame? So similar things than what we worked through when we did the L frame, but here in this case, if I was putting in a column and I wanted that in release, then okay, with the endpoint, so instead of continuous, I would have changed that here. Basically, I'd say, okay, I want to release those rotations and the warping continuity at the end. Now I got my column length, what reference axis do I want, how many elements, I put the column in, and I put the column in only with the length to the bottom of the roof girder. Okay? So now there's another modeling feature that's available in Consteel that's very useful if you're doing something like this. At this point, if that's all I did, then Consteel would not recognize that the column is connected to the roof girder. So I've got to do something to connect it. If I go back to the line view, I'll highlight to show what's going on with that. So if I click right in here between that reference axis of the roof girder and the column, I think I got a point support there also. I'm going to turn that off. I've got what Consteel is calling a connection element. How did I do that? If I come in and I go to this option here of a link element, I need to create a link between the reference axis of the right-hand end of my beam and the top of that HSS column. So it's in effect modeling a rigid link there. So if I clicked on that and brought it up, I could basically say, yeah, I want both of those ends to be continuous because I'm going to model the release in the member that I'm connecting to, and I just go click at the reference axis of the beam, click at the top of the column. I've now got those connected by a rigid link. Now, what's the significance of that? The solution, the results really don't change all that much by this further modeling detail, but they change some. And let's again here we can look at a three-dimensional view of the structure where we've got essentially a three-dimensional rendering of all the members, and we can understand what's going on a bit better. So let's go to the analysis. I've got all the analysis set up similar to what we looked at with the L frame before. So either under a first order analysis or a second order analysis. If I look over here, it's basically, I'm actually got a little more displacement, particularly in my second order analysis. What's going on with that? What do you think? I've been talking a lot. So why do you think that maybe my displacement would be larger at the right-hand end here in this problem, looking at what you see?
We have released warping.
Say it again.
We have released warping at the top, that's why.
You release warping so the in-plane displacements really aren't depending on the warping so much. So it's not that. And we had a rotational release in the model we were looking at yesterday. So it's still rotational release. But again, what we did yesterday, I was putting that pin at the center line of the beam. Okay? So if you run with that for a minute, what do you think changing this model where I shifted that pin connection to the girder down to the bottom of the bottom flange of the roof girder, what's that doing in terms of the mechanics of what's happening here in the structure? What do you think? It's not the torsion. we could look at a buckling solution out of plane, and there might be some things going on there, but here I'm trying to get you to focus on this in-plane response that I'm trying to highlight here. So this is the way this model is working here now. Let me bring up a model that doesn't have this, and that might help you in thinking through it. So this is a model that's more like what we were working with yesterday. Let me get a front view of it. Okay. So when I analyze things here, it's working that way, right? So what's different here, and would cause larger displacements at the top of the HSS column in the other model. So here's what I've got in this case. And if I go to the other model, get that out of the way. So now we've got this. Do you see it? You want me to just tell you?
Load is causing an extra moment because it's at a
Okay, all right. Like a P delta moment? Yeah. Yeah, so notice by doing this, now my leaning column, this HSS column, is shorter, right? The shorter I make that column with the same delta, the bigger P large delta effect. Same delta, short length, bigger P delta effect, right? So that's coming in. Now what's the other thing? Look at what's happening in terms of the lateral deflection of the centerline of the roof girder versus the lateral deflection at the bottom of the roof girder. If I'm connected to the bottom of the roof girder here, it's deflecting further, right? Because I've got a major axis bending rotation that's counterclockwise in the roof girder. If I'm connecting to the bottom, then that point's displaced over laterally further than the reference axis, right? So both of those things are giving me larger displacement at the top of the HSS column than that other model. You know, you might say, well, yeah, does that make that big of a difference? It doesn't make too big of a difference, but it is a difference. Okay? All right. Now, another aspect here, and Consteel, if we went to its design capabilities, would handle things in this way once we go, when we've modeled that joint. So if I go back here, I'm modeling this panel zone with the joint wizard. And so in sizing the wide flange column, or checking it here on the left, it would basically say, well, that member stops at the bottom of the girder, right? I'm not going to model member length all the way to that center line. We've got a big honking beam adjacent to the center line over a finite length there of the panel zone there. So that's really a more realistic assessment in size in terms of sizing the column. I noticed in the Indian IS 800 code, I think it basically said, no, you should always design the member as center line to center line. But here, this would be an argument that in some contexts, no, it would be more appropriate to consider, well, that member goes from the base plate to the bottom of the roof girder. And then same thing for the HSS section over here. It's shorter, a little bit shorter. So okay, that may, here we're just modeling in this representation, we're just modeling the behavior. That's working just as a pin and strut, right? We're not generating any moment in that HSS section. Got a nice, perfect spherical bearing connecting the top of the column to the bottom of the roof girder. Okay. And if we do the checks here on this, we basically find that things are more than adequate. So here's where I want to use the board a little bit. Our gamma critical for this case is 3.74. So that's elastic buckling result. Let's actually look at that. So if I go to buckling analysis, oh, what's that? Oh, the HSS section is buckling. Okay. Okay, that's important for the HSS section. It's not important for the frame design, right? If I set this to a perspective mode, well, let's look at the second mode. Oh, it's buckling out of plane. Okay, it's a square HSS section, so yeah. Oh, this is the one I want for the frame. It's a front view here. Oops. I don't want that buckling mode. So 3.74. So this is my, oh, come on. This is my buckling mode for this case. Clearly that's a side sway buckling mode, right? And I'll just say very broadly, so the axial force in the HSS section here, that's equal to 370 kilonewtons, and the moment in the W section at the top, and this is at the bottom of the girder, 111 kilonewton meters. Okay. So, again, if we look at second order analysis results here for this, we can go to internal forces and we can go to MX. So what I'm referring to here is, yeah, clearly the moment is dominated a lot by moment bending. The big moments is actually in the roof girder. I can, if I turn on the portion manager, I can use the automatic portions here to basically say, I'm not interested in the moment in the roof girder. Let me just look at what's going on in the column and what's going on in the HSS section. Well, no, there's no bending in the HSS section here. It's pin-pin. And at the top of the, or the bottom of the roof girder, there's your 111, okay? All right, so that's a model that often we would use for design. But now let's look at another representation where it's a continuous market shed frame finite joint size. So if you pull that one up, okay, so here's the frame, looks pretty similar to what we just did, right? If I look at the front view of it, there's my front view, but I've now changed this. I basically went in and said, okay, on this column, we'll turn off the portion view, I've now changed the release endpoint to continuous. So I'm saying, yeah, oh, hey, I've got an end plate connection of that HSS section to the bottom of the girder. I think maybe that's closer to continuous detail than a pinned in. So that's what I'm thinking for my idealization. Let's run the analysis. So if you run the analysis that we're set up here, clearly that HSS section, let's do second order. And so if we look at the deflections here, that HSS section is kind of getting beat up by the frame a bit, right? It needs to bend with the major axis bending rotation at the end of the roof girder. So it's bending way out there. And if we assess what we've got with this by going to click on the deformation XYZ, go down to internal forces, and we'll plot the bending moment MX. And again, let me turn the portion manager back on, so view portion manager, and we'll just do the HSS column and the other column. So now if we scale those moment diagrams, clearly that HSS column is, it got a lot of P-small delta effect going on, right? Even though this is a sway frame. So this is what I was mentioning yesterday when I said, okay, well, sometimes you can add material or you can add continuity and you can make a structure weaker. So let's look at what we've got for the buckling load on this. So we'll go back to the full frame, and we'll tone down the exaggerated displacement there a bit. So it's buckling like so. So remember, the buckling load we had with the previous model was 3.74. This is now gamma critical equal to, what, 3.04? What happened? We added continuity, the buckling load went down. Or at least the buckling mode involving side sway went down. We had a lower buckling mode on the HSS section before. So is this side sway buckling, or is it non-sway buckling? Or is it neither? We've basically got a problem, and this is what LeMessurier, when he was doing that inequality I showed you on the with the calculation of what was it, the K factor. He would put a lower limit on the K factor because if he was looking at frames like this and saying, yeah, that stiffness-based model that we use, that's just a side sway stiffness model, stops working so well when we get to a frame that's like this. Let's be careful. Yeah, so it's kind of a hybrid buckling mode involving non-sway buckling of the HSS column, which has some partial restraint of side sway from the rest of the frame, but the rest of the frame is undergoing some sideways sway in this buckling mode. Right? And so the first thing I'd like to ask here is a question. I didn't write out a handout for this, but how many elements do we need to make sure we've got a good model of this HSS column? So if we go to the analysis and second order results and we pull up our internal forces there, we can see that we've got, okay, so 369. Now it's essentially the same as 370. Let's basically still it's essentially 370. And if we need to look up Well, what's the moment of inertia of that HSS section that we use? We can come back here to the section administrator. We can click on our HSS section here, modify. Yeah, moment of inertia is 3.616 times 10 to the 6th millimeters to the 4th. And so if we do a PEL there for that buckling of the HSS section in plane, so I'll call that X. So that's equal to pi squared EI of the HSS divided by that L squared, which was, I think, I'll do L minus the depth d/2 of the roof girder squared. So if I do that, I get 688 kilonewtons for that. Okay, so this was, and for this we get, it's 3.6 meters from base to the center line of the roof girder. So this is 3.22 meters here for L minus d/2. And so, so the PU over PEL here is 0.54. How many elements do you need if you want PU over PE script L less or equal to 0.02? How many elements? Let's try 6. It puts 6 in here, so 6 squared is 36 times 0.02. Did I do that right? Yeah. Yeah, so this would be, that would allow us to get to 0.72, I think, right? So 6 elements should do it. So that's kind of the basic rule, applying the basic rule of thumb that I've been discussing there. And if we check that column, what did we use? Let's see. I have automatic, but if let's look at the okay, here I think this basically shows it 1, 2, 3, 4, 5, 6. That's what you'll see Consteel use is often 6 elements between unbraced lengths or between brace points. Okay, so that looks like that's going to work pretty good, and you can kind of without doing all that, you could sort of simply say, okay, well, let's just look at the moment diagram we get from the analysis. Does it look like it's a reasonable representation? So we're doing a bilinear representation of the moment diagram. Is that look like a pretty good fit to you? It looks pretty good. It's piecewise linear, but it looks like it's a pretty good fit to what is really happening, huh? All right. So the academic question of the day, if we come here to this, and let's come back to where we're drawing the deflections. We can look at it with a perspective view if you wish. So should the continuity help or hurt the HSS column here? So we can see already that the gamma critical was decreased. What's the buckling mode? We can see there's a lot of non-sway or basically non-sway bending, we'll call it in the HSS section. Now if we do a check of the wide flange section there, without writing all the numbers out, we'll get for the wide flange section, so the left-hand column, wide flange column, we'll get a the effective length factor, Kx, is 3.29. This is based on that's based on L equals 3.6. You could say, why didn't we use it to the bottom of the column? Okay, if we did, we'd still get the same KL because the P critical X here is the same number that we're basically, and that's the fundamental value, that's 1081 kilonewtons. And so if we use this with the AISC column curve formula, then we get a VPN equal to 838 kilonewtons and a PU over VPN equal to 0.418. The moment at the top, so for the moment in the wide flange section, VMN, if we work it through everything by AISC standard, you can get to VMP. You got a sufficiently short unbraced length. The moment gradient from 0 to at the bottom to maximum at the top helps. And so VMP here is 249 kilonewton meters. And so mu over phi mn is equal to 0.462. And so the unity check, so the beam column interaction from these, it's the bilinear equation in the AISC provisions, gives us 0.829 for the wide flange column. And so that checks, even though it's a little bit larger than what we would have had if we had designed it based on the simpler model that we were working with yesterday, where we didn't have the finite joint size there considered in the solution. But now the HSS column we get a Kx, if we back solve for Kx, we get a 0.788, and I calculated that one based on L equal to 3.22 meters, so the length to the bottom of the girder. And so here from the solution, for our loading that we have, the P critical X is 11,008 kilonewtons. VPN, if we do the column strength by the AISC column curve on the HSS section, is 0.618. VMN The HSS section here has compact wall elements, and so we got VMN equals VMP. So that's equal to 31.2. It's not very big, so the plastic moment you can see is relatively small compared to what we had for the wide flange column. And mu over VMN here is 0.658. And the unity check, so here this would be by AISC, would be unity check equals 0.618 plus 8 over 9 times 0.658. So we get 1.203. All right. So we had a column that was perfectly good with the other idealization, and now it's failing by 1.2. Okay, as a pricing engineer, what do we do about this? Again, as I said yesterday, this is the problem where Balint said, "Oh God, if you're going to do that." But this sort of situation, it does come up in practice in various ways where you have something, usually something relatively small that's starting to get beat around by the rest of the structure. So again, in structural stability, we don't necessarily increase strength when we increase continuity or when we increase material. Change the idealization. I think probably the detail at the top of the column is probably closer to fixity than actual perfect pin, right? So it may be hard to argue for that, although many engineers have said, "Oh, come on, I'm just going to design it as a pin and strut, forget about it." We could use a larger HSS column. If we go there and we start doing that, what's going to happen is that this is the type of problem where we make the HSS column bigger, it attracts more moment, and the unity check gets larger until it gets big enough where it's not a problem. Now, clear, if we had wide flange sections that were equal on both ends of the frame, then life would be good, right? But then Mr. LeMessurier wouldn't like how his storefront looks on the right-hand side. Sometimes you might get away with, oh, make the HSS section smaller. And the unity check reduces if you can get it to work. But then there's another approach, and that's this actually shows up as kind of very intrigued with how the Indian standard spoke very directly about it. We don't have that kind of guidance in the American standard. That's like, well, wait a minute. Do you think the column base is really a perfect pin? So let's say, well, no, we don't. So let's go to a third model where we're going to put in a rotational spring to represent some incidental restraint that we would get from a simple column-based detail. So as I understand it, in the Indian code, it doesn't tell you how to model column stiffness, but it makes a comment about you should use 10% of the column stiffness. And we have a rule that's kind of doing that when we do buckling calculations with the alignment chart in the AISC provisions. And with the alignment chart, we basically say, oh, if you have a pinned-in detail, use G equals 10, which is your EI over L of the column by the EI over L of the beam. Well, there is no beam, but we're saying, oh, it's a rotational spring equivalent at the base. So that's kind of the same thing as what the Indian code is saying. Now with side sway, the column stiffness that's associated with this side sway mode would be a 6 EI over L. So we're going to basically say, okay, so we should use a rotational spring. I'll call it a little k, another k, a k rotation, equal to 1/10 of 6 EI over L. So 0.6 EI over L. Okay? And so this is a kind of a silly little way of saying, okay, let's count on some restraint. If you start modeling more directly what's really going on in a base detail, you typically find that this is probably a very small number from what you get at low load, but then at some point the simple base detail starts rotating a lot. It's a nonlinear response, but we're trying to do this without getting into some modeling a nonlinear base response on the frame. Well, how do we do this in Consteel? If we come to structural members and go into the point support again, under the point support, we can go to an option. I've actually created an option here for the wide flange section and for the HSS section. If I click on that to understand what it is and pull it up. Okay, so I called it XYZ, ZZ, RY, W section. Okay. And so I've got XYZ fixed, rotation X. So that's a horizontal axis, so out of plane. I left that as free. But then for RY, rotation about the global y-axis, I calculated the 6 EI over L of the column and put that in here. And so now my base model has this fake elastic spring that's kind of an accepted kludge of, okay, let's put in some restraint effect for the base. Okay. And if we go inspect this, I'll turn off the portions dialog and I'll select the column. Is that what I want to do? No. I want to actually select the base detail there, and I can see, yeah, there it is. That's for the HSS section. If I click on that one, I can see, oh, the HSS section 0.6 EI over L is much smaller because that's a much smaller section. So if we use that as our idealization for the wide flange section column and for the HSS column, let's do our analysis, and let's go to second order, and let's look at our internal moments. Again, the girder moment kind of dominates everything, so we need to go back to turn on our portion manager. And let's just focus in on the columns. Oh, I've got almost full reverse curvature bending in the wide flange section here now. That's not because, notice that there's more going on here than just the side sway. A big part of what the moment in the wide flange section is the gravity moment coming in from the roof girder. So that combined with the lateral moment from the side sway, we end up getting some moment diagram in the wide flange section that's almost full reverse curvature bending, even though that's a very flexible connection model at the base. And I'm getting a little bit of help in the HSS section. So now, that's where I need a different color chalk. So we had 3.04 for the side sway buckling. Let's look at what we got here with this. Buckling, okay, it's gone up to 3.8. And still, if I put everything in, it's still kind of a side sway mode with a big influence of a non-sway buckling going on in the HSS. But that's 3.8 is slightly higher than the 3.74 we started with when we just had a basic pin-pin model of the HSS, right? And so based on that, if we're looking at the wide flange section column, so the W section, I end up now with a KX 2.94, and which based on 3.6 length, which gets me to a unity check, if I put it all together, of 0.46. The moment went way down, so the unity check on the wide flange column is much lower now. All right, if we look at what we're getting from these things, so if I just change the numbers here on the HSS column where we're having the trouble, this becomes 0.707 now from the buckling analysis. This number, which is the fundamental number for the column buckling and for getting the column strength, becomes 1376. My VPN is 0.618, that's not right. VPN, I wrote down the ratio there. PN was 590 before kilonewtons, and PU over VPN was 0.618. So now with this change, where we've got this simplistic modeling of the base conditions, this becomes This becomes 632. This becomes 0.577. And the VMN is still VMP, but the moment decreased a bit. And so MU over VMN, this reduces to 0.54. And the unity check, if we put these in, so I've got a 0.577 here, 8/9, 65854. And this becomes Oh, crap. We still didn't quite work, but we're close. So at this point, if you're willing to buy that, this is a reasonable elastic estimate. If you really dig into studying base restraint, you find at low load levels, this is a very conservative, very low number. It's just that if you get to a very high moment demand on the base, it's nonlinear, and so this is kind of trying to give a very simplistic secant approximation for the base rotational stiffness. So given this, you could probably at this point just say, okay, maybe we'll just make the wall of that HSX section a little bit thicker, and then it's going to work. Okay. If we make it a bigger section, we're probably still going to have a little bit of trouble with. If we make it bigger, we're going to attract more moment. Okay. So, kind of a little interesting case there that it's kind of useful to think about. For those of you in practice, have you encountered cases where you basically are trying to design something and you make it bigger and say, wait a minute, now I've got a bigger problem? Okay. It happens sometimes. So this is a kind of a simple illustration of this. So here, if we look at the center line of the roof girder for reference, so it's drifting under our factored loading by 54.8 millimeters. Okay, here and this is with the base restraint. Without the base restraint, let's see what we've got. So I think this is the one without the base restraint, continuous. So we have 54.8, it was 79.7 here. And if we go back to our simpler model that we started with, where we just say we're going to model that HSS column as a pinned in strut, I've got to do deformation. Okay, 87.8 there. Okay. So let's see. So did it increase with the second one or no? 87.8 here, and then when we went continuous, no, 87. Okay, so it did. By making it continue, that makes sense. The continuity did decrease the lateral displacement a little bit, right?